parameter estimation. We consider here a bounded error estimation problem. It is defined as follows. I have a model here, P1 times exponential P2t, so t is time, and it should belong to some intervals. These intervals are measured for different time t. Here I have t belongs to a set capital T and is composed of four numbers, t1 which is equal to 0.2, t2, t3 and t4. It means that I have four interval measurements. The four are given here and I have the corresponding intervals on the right. I define the set of all feasible parameters as the set of all p inside a prior box, -3, 3, and it is a set of all parameter vectors that are consistent with my measurements for all time t belonging to capital T. The first thing to do is to show that it is a set inversion problem. So to do this, I will represent here time t, and here it is the measurement space, the y space. I have some measurements bars, 4 like this, for instance. In my situation I have 4 measurement bars, and this one is for t1, so in my situation is 0.1, here t2, t3 and t4. Okay, so t4 is here. Here I have an interval which corresponds to y of t1. So this interval corresponds to this. This will correspond to y of t2 and so on, y of t3 and so on. I will have a parameter space. The parameter space I will represent here, for instance. Here I will have P2 and P1. So it is a set of unknown. So for some parameters, let's say this one. I will represent red. This one. I will have an exponential because my model, I recall that my model is P1 exponential my minus or P2 t. So it means for this one, I will have an exponential which will be like this. Okay? So this one is consistent with all data bars. If I take another one, for instance, this one, I will be consistent with some data, for instance, with this one and this one, but there is at least one data I am not consistent with. Then the set of parameter vector I want to find is a set which contains all parameters that are consistent with all my data. So why it is a set inversion problem? Because all these bars correspond to an interval, and the Cartesian product of all these bars is a box in R4. So I will try to represent it here. have here my parameter space p1, p2, and I will have here my R4. So here I am in R4, and I have an interval here which correspond to so this interval corresponds to y of t1, and here I will have r of t2, and there I will have y of t3, and of course I'm not able to represent here y of t4. Okay, so now if I have a function f which maps R2 in the measurement space R4. So if I take one point here, by f, it corresponds to a simulator, I should fall inside this one. If I take a bad one, I fall outside this box. P corresponds to this. So this is P. And my function f of P1, P2 corresponds to exponential, so P1 exponential P2 T1, and so on, P1 exponential P2 T4. Okay, so you have four numbers. F maps R2 into R4. So it is clear that here P corresponds to f minus of y, where y is this box, and I have also to do the intersection with the previous box, which corresponds to minus 3 square, so the prior box. The prior box could be, for instance, here, a box which encloses all solution, or a part of the solution of the inverse, but here I will assume that it is large enough to enclose all my solution. Otherwise, it contains some prior information which are given under the form of a box. Question number 2. I have to implement later the CV algorithm. So it will be on question number 3. And for this, I will have to manipulate boxes. Should be able to compute the width of a box, to bisect it, and so on. So first, I have to implement this library, mybox.py. Of course, I will use Python, and I recall that I have already my own interval library, which is given here. So maybe I will do some copy-paste for the other one. Okay, I will keep this. File new, file save as, and I will call it my box. Paste. Okay, so of course I will have to remove plenty of things, and I will use my math. Okay, I will see this later. I remove this. uh, and this will be called box. Then I import math and I will use also interval. So from my interval, import everything. Many of things will be removed here. So for instance, I will don't need this and so on. I don't know yet, but I think I can remove many things. I will see later. Okay. Uh, I will first explain what I want to compute in this library. So a box, a box, I will represent here, will be considered as, for instance, this one. We'll have some components. So it will be the x component given here and the y component given here. So here I will have x and y. So I will represent only two-dimensional boxes, x and y. So a box x will have the component x1, which will be an interval, and x2, which will be the other interval. So probably here I will call them x and y because I will only handle two-dimensional boxes. I will have to bisect them. So for this, I will have to define the width of an interval. So the width of an interval will correspond, in this situation, I will take the largest one. So here it will be this. And this corresponds to the width of x. From this width, I will be able to define two boxes. The left box, so this one will be called the left of x, and this one will be called the right of x. So this one in orange corresponds to the right of x. So here, imagine now that I have a box which is like this in the other direction. And of course, the width will be will correspond to the vertical. So the width will correspond to this. Excuse me, to this. And the left will correspond to this box. And the right will correspond to this box. So it depends, of course, of the direction which correspond to the width. That's what I want to implement now. So in my box, in my library, box, my box dot py, I will define the class box, and this box will have several methods. The width of an interval, the left the left and the right. And to do this, I will also have to implement inside my interval .py. So why I have to do this? Because the width, the box is a Cartesian product of two intervals, and to compute the width or to compute the right or the left of a box, I will have to do the same on its interval components. So let me remove in my box what I don't need. I don't need this, I don't need the log, and so on. Box. First, about the initialization. I will write by a capital like this, X, A, and B, and I will only write X dot X and X dot Y, so the interval components will correspond to A and B, which are two intervals. So it is a way I will initialize a box thanks to this keyword, which is the constructor keyword. When I want to print a box, I will write as follows. I will write the two interval, and here I will put a X just to recall that it is a Cartesian product. Here I will have the X, X because it is my box. I take the X component, the lower bound, and it will be written here. Here. Okay. I will have the second one will be the upper bound. And I will do the same with the Y component. Y and Y. So it is a way I will I don't need this parenthesis. It is a way I will print an interval. I now define the width. So let us define the width. Of a box X. First, what happens if this box is empty? So if X dot X is empty, or if the Y component is empty, I should return the width of an empty set, and by convention it is minus infinity. So return minus infinity. So this symbol is defined inside my interval. Else I should return the max of the width of the two interval components. So it will be X dot X dot width. So I recall that it has not been implemented yet. I will have to do it later. And for the Y component, once I have defined the width, I will have to define the left of an interval. So left of a box, left of X. I will have two different situations. First, so here this and this. Two different situations. First, if the width corresponding to the x component is greater than the one corresponding to the y component, then I should return a box with two intervals. So the one corresponding to the y component will not move, and the one here will correspond to x dot x dot left. So the left of the x component. Now so here I will have else. I should return a box x dot x and here the left with respect to the y component. Okay, now I will have to do the same with the right. Copy paste, right, if the width of x is greater than the one of y, I will return here x dot, so it will be here right, and the y component will not move, otherwise the x component will not move, and here I will need right. Here def width of x, return x dot upper bound minus x dot lower bound, and I will get the width. Now about the left of an interval, so I bisect it and I will return an interval, the left part interval. I will keep the lower bound, and here I will compute the middle. So the middle is 0.5 multiplied by x dot lower bound plus the upper bound. Okay, interval and for the right interval, so it will be I will have to invert the two of them, so here it will correspond to the middle, and I will keep the upper bound. Of course here I need the two dots. I have now implemented my own box library, and I will be able to solve my parameter estimation problem using the CVIA algorithm, set inverter via interval analysis. I will now have to use Python and vibes for drawing, and also our own interval and box library to compute an inner and an outer approximation for P. So for the set of feasible parameter vector. So to do this, I will go with Python here. Maybe a copy paste will be useful. This part, up, file new, file save as, and I will call it my estimator. Okay. So what do I need here? I don't need a lot of things. I need my box. Okay, in my box I have my interval. I will use also vibes. So from vibes, from vibes import all. I don't need to build any new class. And I will need this. Okay. So what happened here? I will also file open for vibes. I will use my minimizer because I have already used vibes in my minimizer. This part will be useful. Okay, and this I don't need. I will put my own program here. What about what is asked here? To solve my problem, I will have to build this set T here and to enter all my interval data first. That's what I will do now. So T equal, so it will be a list. The list will take all, so T1, T2, T3 and T4. So I have 4 times. Y is also a list of intervals. Interval, the first interval corresponds to 1.5, 2, and I will have 4 intervals. The second one is 0.7, 0.8, then 0.1, 0.3, and minus 0.1, 0.03. Okay. My prior box P is a box which is composed of 2 intervals. The first one is minus 3, 3, and the second one also. So it is my prior box. Then I will call CVIA. So CVIA is not programmed yet. will have to do it now. Civia, and I will enter P as a parameter. I will put my Civia here. Def P Civia of my box P. So for the Civia, I have to take boxes like this, and to check if the image by F is outside or inside this box. So it will be either inside or outside, or I don't know. But I will try to get a better representation like this in the YT space. So the box now corresponds to 4 interval, and the Cartesian product of this 4 interval corresponds to a box in R4. Now if I take a parameter vector here, excuse me, here I will take a parameter vector in the P1, P2 space like this. Then this by F, it will go in the, I will build a box so I can be consistent with the first box, maybe for the second one, outside for the third one, and inside for the last one. Let's say I have this. So in this case, it means that the box corresponds to the situation here. I am outside. I am consistent with some components, but with some other I am inconsistent. But with this representation, I have some more information. So here, so I have P1, P2 space. My box is mapped by F in R4, so here it is a representation of R4 with the 4 components. For the first one, I am consistent with the first one. So here I will put 1. For this one, I don't know, so it will be 0, 1. 0 because I am totally inconsistent, and here 1, and I will count the number, I will sum this interval, so I will do 1 plus 0, 1 plus 0 plus 1, and I will get 2, 3. So it means, this interval means that I am consistent with at least 2 of the intervals, of the data interval, and at most 3. So at least 2, at most 3. If I get 4, it means that I am included, so it will be true. If I get something smaller than 4, it means false. But this representation contains more details, not only equal to 4 or smaller than 4. And it will be useful to deal with outliers, as we'll see later. Let me come back now to my Civia. I will do in my Civia how it works. I will do a test. B equal test of P. And B will be an interval. It will be similar to the interval 2, 3, which is given here. And it will contain the number of intervals I am consistent with. I will program it later. If B dot upper bound is smaller than the length of y. So here it will be 4. Then what should I do? I will vibes dot. I will draw the box. Draw box. Red. P dot x dot lower bound. P dot x dot upper bound. So it is for the x component. And now I will do the same with the y component. And the color, no, if I am smaller, it means that I am false. So I will have to draw it blue. It is a convention. Blue like the sea. The sea is blue. It means Earth is red, and the beach is yellow. So red means inside, blue outside, and yellow I don't know. Cyan. Okay. Now else. Else if. The second condition is if the upper bound, if the lower bound is greater or equal than 4, so the length of y. And I will do the same. But I will paint it red. So when I write it between square, it means that it will color only inside. Now, like for the Sivia, else if the width, so it will be the width of P smaller than let's say 0.1, a small value, then I will draw it yellow. Yellow, and because it is small, I don't want the border to be black, so I will put yellow. So it means the borders here, and inside is a second yellow. Now, last condition, else. Else, I don't have to draw it, but I will have to call Sivia again. So Sivia P dot left Sivia dot right. Now I will have to program my test. Test. Test of P. So I have to count the number of intervals I am consistent with. So at the beginning, interval, it is 0, 0, because the upper bound and the lower bound for the number of interval I am consistent with is 0. So P interval 0, 0. So I will count for all intervals, for all E in range of the length of Y, for all my intervals. What should I do? Up here, double dot, here also. I check all here. Okay. So what should I do? I will write ti equal to t of I. The same for yi equal to of I. Then I will compute fe. So fe corresponds to p. So it's my model 2.x multiply by exponential of te times p dot y. So it is my model, and it is a if component of the function f. Now I will have two situations. If subset of fi yi, then b dot lower bound will be incremented. B dot lower bound plus 1. I have not yet programmed this subset. I will do it later. If not, so if it is not disjoint, so it means not disjoint. It means that intersection is not empty. Again, I will have to program later disjoint in the interval library. So the upper bound will be incremented by 1. And now I return the interval b. Okay. I have almost finished. I have to go to my interval library and to implement disjoint and subset. So I will write it here. Def subset of x and y, and then def disjoint of x and y. For the subset, I will first check if x dot is empty, and in this case it means of course empty set is the empty interval will be included in y, so I have to return true. Else I have to return so I will check if the lower bound, if both the lower bound and the upper bound are included in y, it means that it is true also. So x dot lower bound in y, and the same for the upper bound. Okay. About the other one, disjoint. I will compute the intersection of x and y. intersect will be this one, but I have not programmed it yet, so it will correspond to the intersection. And I will check if the intersection is empty. It means that x and y do not intersect. So to program this, I should overload this symbol, and it will correspond to the n. So let me put it, for instance, there or here. Okay, with the operators. So definition, I will copy paste maybe this one. Oh, okay. So here I will overload end. End means intersection. If x is empty, if one of them is empty, of y is empty, then of course the intersection should be empty, and I will return the empty interval. So interval of 1, 0, for instance, which is empty. Else, I should return interval of max, so the maximum of the two lower bound, and also the mean of the two upper bounds, which corresponds to an intersection of two intervals. Upper bound, upper bound. So here I have to add, of course, the two dots. Let me check here also the two dots. What else? About maybe I check everywhere the two dots. Here it's a mean, of course. And I will come back to my estimator, and I will be able to run it. Maybe yes, here a two dot problem, two dots, and there drawbox, drawbox, drawbox. Okay, let me start it. Execute. Vibes give me the following set, and here I have the set of parameters, which is around -1 and 2. As explained previously here, now I don't want to be consistent with 4, exactly 4, but I want to relax a given number of intervals. For instance, I want to be consistent with 3 intervals or 2 intervals, so I want to allow a given number of outlier, q. If q equal to 0, it means I have no outliers, I want to be consistent with all 4 intervals. If q equal 1, I want to be consistent with all intervals except 1, and so on. That's what I will do now. I come back to my Python program, and there I will, in my CV algorithm, I will put q equal 0, for instance. So 0 outliers, it will not change anything. Minus q, because I want to be consistent with all except q. And if I do this, on my vibes, nothing has changed. Okay. Now, if I want, if I put q equal to 1, vibes will give me a larger set, which is given here. So it is a union of two sets, and depending on if I am here or in this set, I will not be consistent with the same intervals. If I put q equal to, then I will consistent with all of them except 2. So it takes more time to draw, of course. Here it corresponds to maybe solution, but maybe also to a bad conditioning due to the exponentials. And if q equal to 3, so it takes more time to draw, but I obtain, of course, I need to be consistent with only one data bar, so it becomes the set of feasible parameter becomes huge. I will come back to q equals 0, and let's come back to the, so of course I have modified the program to be consistent with given number of outliers, and I will solve my question number 4. I mean, I want to draw in the YT space an enclosure for the output, so for the set of all t and y that are consistent with my parameter set. So after my Civia, I will add a new function which corresponds to draw output. I will enter a parameter p. T will be equal to 0. For instance, I will start with 0, and dt, so the sampling time, will be equal to something like 0.05. Okay, a small number. Then to draw my figure, I will have to put several figures. A figure will correspond to P, and about the properties, maybe something smaller, because I will have two figures. So let's say 800, 500. Okay. I will have also a new figure which corresponds to y, and the properties here, let's say 700, to be just on the right of the first one, and the size will be about the same. Now, when I have draw a figure, I will select, so vibes, I will draw on the figure y, so vibes dot select figure of y. While t smaller than t max, it's 5 because t4 corresponds to 4 in my application. T equal interval of t t plus dt, because I want to enclose all t inside my sampling interval. I will compute y. The interval y will correspond to p dot x multiplied, so it's my model, exponential to t multiplied by p dot y, it corresponds to p2. And I will draw the box. So copy paste, draw box, t dot lower bound t dot upper bound, y dot lower bound, y dot upper bound, and I will draw everything, for instance green, even the border, green inside and green in the border. And there I have to do t equal t plus dt. So here I draw an output which corresponds to p. So when I have something like draw yellow, I will have to call the draw output of p. Here, when I will draw my boxes, I have to select the right figure, so vibes dot select figure of p. And once I have finished all, I want to see my data bars. So I will go at the end of my program and I will select. So copy paste, I will take this one. Once I have done this, I will select the figure y, and there I will draw my data bars. So I will take, for instance, this one, copy paste, and I will compute for all my data bars, so I in range of the length of y, I will draw t of I here. So here it will be a small number, so I will draw a small box, so minus 0.05, just to see it. Plus 0.05. Here I will have y of I dot lower bound, and here upper bound, and I will draw them red. Red and red. So let me check here, of course, double dot, here only one lower bound. I execute. I obtain my two windows. The first window corresponds to my parameters, and the second window corresponds to the tube which encloses all outputs, and here I can see my 4 interval measurements. So we can see that sometimes the data bar is larger. So if I want to filter, I have to intersect. So to filter means to have more accurate interval measurements. I have to intersect the red bars with the green tube, and I will contract it. So this one could be contracted. Of course, it contains some negative values, so it was clear that these values were inconsistent. But it is also the case here. It is not the case for this data bar, and probably this one can be contracted a little bit.